Final project, simple engine design, stress, and thermal analysis. Understanding piston engines has always been a daunting task requiring an extensive amount of knowledge of heat transfer and how different materials affect outcomes. With the invention of computer-aided design tools, we now have a deeper understanding of how it all works. Using different simulation techniques, we are able to rapidly create extreme scenarios where the components of an engine are tested and analyzed to make sure they are built to withstand the required conditions. With the simulations being conducted by advanced computer models, these results can be obtained without having to assemble the engine physically. This allows for a high level of experimentation with different materials, dimensions, and tolerances, with rapid results yielding efficient designing processes. In this case, using SOLIDWORKS to perform a heat transfer study and a design study, we can use the results to determine the thermal impact, temperature distribution, mechanical forces, and material limitations.
Team member introductions. Ariana Terracino is a mechanical engineering student and set to graduate fall 2026. She enjoys reading and swimming. This is her bird, Marlo.
Lysander Temprana is a mechanical engineering student and is set to graduate fall 2026. He enjoys building and racing cars.
Marcel Fernandez is a mechanical engineering student and is set to graduate fall 2026. He enjoys designing parts and 3D printing them.
The general simulation settings are default standard solid mesh with a force of 2,622 pounds. The wrist pin, block, and crank are made with 1045 steel, and the piston and the rod are made with 6061 alloy. And the piston and rod are made with 6061.
The static study setting, the piston compression setting, the external load 2,622 pounds of force downward on the top face, fixed geometry on split line 3.
For the pin compression, the force is downwards on the top half of the midsection segment and fixed geometry on bottom halves of the outer segments. For the bending crankshaft, for the torsion crankshaft, the external force is applied on the top half crank arm segments and the fixed geometry on bottom halves of the outer pins.
For the connecting rod static study setting, both are fixed geometry on split line 2. Both have the external load 2,622 pounds of force downward direction on split line 1, and the max angle is 23.57.
Using the static study settings shown earlier, we have the shear stress displacement and strain shown and a factor of safety of 1.5, meaning the pin does yield. Therefore, we have to do a buckling study of the pin, where we find the loading factor to be 330.01. The critical load and critical stress are shown. We did a design study on the wrist pin since the factor of safety was 1.5 and we wanted it to be over 2. For the first design study, we found an optimal diameter of 0.69 inches but wanted a more exact value, so we did a second design study where we found an optimal diameter is 0.6 inches. The factor of safety at this diameter is 2.176. For the crankshaft bending study, using the static study settings shown earlier, we got the max pin shear stress, displacement, and strain shown, and a factor of safety of 8.2, meaning that the crank does not yield. For the torsion study of the crankshaft, we got the stress, displacement, and strain shown, but a factor of safety of 0.71, meaning the crank does yield in this scenario. Therefore, a buckling study had to be done, where it was found that the loading factor was 437.9, the critical stress and critical load were determined and shown.
The piston compression study, the max stress, max strain, and max displacement is shown. The factor of safety is 2.1 and it does not yield. For the connecting rod compression study, max stress, max strain, and max displacement are shown, and the factor of safety is 0.33. In this case, the piston rod will yield. The connecting rod buckling study, the load factor is 6.3587, the critical load is 16,673, the area is 0.37 inches squared, and the critical stress is 45,061. The connecting rod at max angle compression study, the max stress, max displacement, max strain are shown, and the factor of safety is 0.24, and the maximum degree is 23.57 degrees. The moment is 3,015.3 inches pound, and the distance is 1.15 inches. The piston thermal study steady state, the max temperature is 648.2 Kelvin, the minimum temperature is 383.1 Kelvin, and the transient state, the initial condition, is the ambient temperature, which is 293.15 Kelvin in all surfaces, and the transient state, which lasted 120 seconds with 20 seconds increment with the initial conditions. The temperature load is 648.2 Kelvin on the top surface only.
For this project, we were able to create various studies to examine all the components of the rudimentary engine assembly. As previously stated, this engine assembly consists of a piston, wrist pin, connecting rod, crankshaft, and engine block. These studies allow us to find both the structural and material limitations for each component, not only to verify if the components will survive normal operation, but also to find the operating limits. With the factor of safety, we can see when these components reach the failure threshold. Using tools like these simulations allows for a more efficient design process and the ability to predict reliability, especially for advanced mechanical systems with many different components that can be potential weak points. Design studies allow for optimization or improvements to existing models. This can be completed by gradually altering certain design aspects of the model in order to find the most efficient configuration. Design optimization is done to maximize the performance of the components without any major design changes. Thermal studies were also completed to find the relationship between temperature and the parts within the assembly. Simulating how these temperatures travel through certain components is vital to the longevity of these components. Thermal studies can simulate how materials expand and contract in relation to other parts, as well as how their strength and fatigue is affected over a period of time. It can also show how quickly heat can travel through different materials and shapes depending on the heat sources, in this case combustion and initial conditions.